Today we are going to go over generative adversarial network. So the overview of the topics is I'm just going to go over the basics of GANs again. If you go over the lecture by Ben, you'll see that Ben has already covered most of the basics, but I'm just going to go over, give an overview again, and give two examples of types of GANs that you can also use in your project and might be helpful there. Then Simral will present the Earth mover distance and Wasserstein GAN, and then we have a notebook implementation of GAN. So the first basic idea is generative modeling. Generative modeling in general is that if you give a bunch of training examples, you want to estimate the distribution that generated those training samples. And so there are two basic things that you can ask your generative model to do. First is density estimation. And from a collection of points, you infer the density of the function that generated those points. And the second is another thing that you might want GAN to do is, or a generative model to do is to learn a function or a program that observes the training data and is able to generate more samples from the same distribution as the training data. And so the basic idea is, given a bunch of samples, you want to understand the underlying distribution that generated those and be able to sample from that distribution. Generative, the GAN actually lies in the second part where we want to create more samples from the density function. So for example, given a bunch of images, like a data set containing a bunch of images like ImageNet, you first understand the underlying distribution, where are all of these images coming from, and you basically generate more such images. The second basic idea is of adversarial training. Adversarial training is a more general idea and was there before GANs were introduced. And GANs are a specific type of adversarial training. In terms of GANs, training a model on adversarial training means that you train the neural network to generate adversarial examples by giving it adversarial examples. So in generative adversarial models in GANs, this is basically done by two neural networks where they act as two players in a game which are playing against each other. And it is called adversarial training because in the worst case, your input is coming from another player in the network, which is not real, and so you actually want the network to be able to distinguish between whether it's an adversarial example, whether it's generated by the network, or whether it's a real one. So this slide basically explains the general framework of adversarial training in GANs and how GANs does the training. So given an input sample X, so before that, it consists of two parts, where one is the discriminator and the other is the generator. Generator generates more images or more samples, and discriminator just tries to distinguish whether a given input is real or fake. So if you look at this flow chart, and this the input samples are, for example, images of face images of people. On the left side, you have a real image, and on the right side, you have a generated one. So X, if for example, X is taken from the training data, it's real. It passes through a differentiable function D, which has some parameters, and it updates those parameters during training. If X is from the real data, you want D of X to be as close to 1 as possible. So the discriminator outputs a probability of an input belonging to a real is real or fake, and 1 meaning that it is real and 0 meaning it's fake. And so you want d of x to be as close to 1 as possible if x is real. And the generator works in a way that it starts from an input noise z. You sample the noise, and this noise basically means that every time you are sampling, you are generating a sample. It starts from a different point and generates a new generated sample every single time, and not if you start from the same point every single time, you'll end up with the same image, real looking or very bad image. So you pass the input noise z through a differentiable function g. G also has parameters and updates during training. And so g of z is something you want, the discriminator wants d of g of z to be as close to 0 as possible, since g of z is a generated one and not a real one. D tries to make d g of z near 0, while g tries to make d g of z near 1. So g is always trying to fool the discriminator to be able to say that what image, the generated image, on the generated image, the discriminator should say 1, but it's 0. So they're always playing against each other, but together to make up a network that is able to generate real looking images. You can also think of discriminator as kind of a harsh teacher, where it's where the importance is that its presence enables the generator to come up with real looking images. And GANs, the basic idea of learning this is GANs are normally used for high dimensional data, where for example images or audio waveforms or videos, where it is very hard to understand the basic or underlying distribution since it is so high dimensional. And here are in papers, in slides or in papers, normally people demonstrate the results on images because it is easier to see results on images than on waveform, on audio or on video. And so with this basic understanding of how this discriminator and generator are working together in GAN, I'll move ahead and give you some examples of different architectures that have been proposed and have given good results in sampled fake images. So the DC GAN was proposed in 2016. In ICLR, I have attached the link of the paper. You can go ahead and look at it. And if you are doing the task of phase generation, then this might be really helpful because the model is easier to understand than many other models. So in the slide, I have only attached the generator part of the architecture. So it first takes a 100-dimensional z, which is this input noise z, and the architecture projects it into a convolutional representation with many feature maps. And here there are almost 1024 feature maps in there, and then it passes it through 4 convolutional layers, and the end result is a 64 by 64 by 3 pixel image. And as you can observe that the number of filters in these convolutions decrease over as you move along, but the resolution size of the image keeps on increasing. And at the end, you can also change the 64 by 64 into other image sizes and have a high resolution image. And as they note in the paper, they are not choosing any connected or fully connected or pooling layers. And so the DC GAN was initially proposed for images, but they have been used for other applications as well, like phase generation and scene modeling, where they showed results that they generated images of bedrooms in different conditions, and they showed that it was able to capture the very slight details of a bedroom window and where the light source in the bedroom is, whether it's coming from the window or it's a light bulb, and it's very interesting, and you should go and read the paper. The other one is called Pics to Pics, and I've attached the paper. It's from 2018. And it's basically image to image translation. So what we have seen before is the generator starts from an input noise Z and then goes ahead and produces a sample. But in this one, it also conditions it on another sample X from the training data. And so what it is able to do is, given X from the training data and an input noise Z, it is able to do something with the sample X. And what that something is, it can do image to image translation, it can, so edge detection and background vanishing and all of those things can be done with this. So I have attached an article that explains this very well, and they have a GitHub repo as well. You can go ahead and look at that. And if you are using this for any of the projects as well, I'll recommend this. So I'll explain the generator architecture for this model. They basically use a unit-based structure where, so this is what their generator basically is. But in each of the individual, these blocks may be convolution layers in themselves, but the basic architecture is like so. That it forces the information to pass through a very small bottleneck layer, and then it projects it to a high dimensional again. And what this does is it forces the input X to be projected into a very small latent representation. The idea being that a finite amount of information can pass through. If a finite amount of information can pass through, the network is forced to learn an optimal reduced mapping, and it does not simply memorize the training data. So because you are forcing the network to have a very small feature representation for your input X, this prevents overfitting to the training data. And if you remember, in a face verification, you were also struggling with what should be the latent representation size, the feature representation size for your faces. And if you went high up, it was more prone to overfit to the training data. And if there was an optimal range of the feature representation size. And you should go and look what they did, because they also worked on images basically. And if your project relates to face generation or something to do with images, you should go look at this. Another part is, so their discriminator is also very interesting. They use a patch GAN to do the discriminator part of it, like a patch network, where you do not look at the whole generated image, like given an input X to the discriminator where it could be real or fake. It does not look at the whole image to decide whether it's real or fake, but it looks at a patch of the image and a different patch every time. So the patch scans of the image makes a prediction whether it's real or fake, and then the mean of this is optimized. And so, as I said, this has been used in image coloring, in background masking, and if you can mask background in images, you can do the same in video processing as well, where different frame in the video, you can mask the background in different frames of the video. I've attached an article here. Will this work? Okay, this explains the background. Oh, it's not working. Okay, so the link does not open up here. I can see it though, but you can go ahead. No, I clicked on it. The browser opens here, but it does not open there. Anyhow, You can go look at the link, and it's very cool. They explain the process of how they're doing it and applying it to video processing. So I'll just show you some very cool results that GANs have been able to produce recently. These are all fake people. These are all fake images of people. They're not real people. The one on the right, yeah, these two people, they I took this example from a paper by NVIDIA, and these are very high resolution, unreal people. So it is pretty cool what they have done with this. And there's this website, thispersondoesnotexist.com, and if you go on it, it generates a fake person every single time you refresh it, and a new fake person. I'd like to show it, but I don't think it'll open up. I mean, it opens up here. But if you actually go and look at it, it's pretty cool. If you refresh it, it generates a fake person every single time. And according to the author of this has implemented the NVIDIA architecture, which is, I've linked the paper. And basically, according to him, a 12-dimensional vector is used to generate a new facial image every single time. And if you think about it, that's pretty cool. Okay, I'll hand it over to Sumo.
Can you use mine? Mine is already dead. Can you use mine then? Do you have to switch it on? No, it's on. Okay. Wait. Yeah. Never mind. Okay. Hi everyone. So we'll be continuing into types of generative models, but before that, we'll take a step back and go into the basic probability theory that was behind all these generative models. So we know that when we talk about generative models in general, we start with an unknown distribution, which can be called as PR, where R is for real, and we want to estimate or approximate this distribution using an already known distribution, P theta, which is parameterized by theta obviously, and we want to transform this P theta distribution to approximate this PR distribution. So that's exactly what GANs are doing basically in general. So how do you do that, this transformation procedure from P theta to PR? So there are two approaches for that. First one comes out to be like, let's assume that your P theta is a differentiable distribution and differentiable function. That means that you're estimating it through a probability density function. And we will have to be learning this differentiable function of P theta so as to model PR or approximate PR closely with it. By optimizing this P theta distribution, how will you approximate PR? How can you make one probability distribution come closer to another to approximate it? So one way of doing it is optimizing it using maximum likelihood estimation. The second approach is when you're using another function, which is G in here. G is a differentiable function which is trying to transform kind of a common distribution Z into, so that it transforms Z into P theta. So we'll get into more details in the further slides, but let's discuss these two approaches in further detail now. The first one, optimizing P theta to estimate PR directly when we assume that P theta is a probability density function. So how do we do that? As we talked about, maximum likelihood estimation, which is done by this equation that you would have gone through in your 601 lectures a lot of time. So this maximum likelihood estimation is kind of close to estimating or minimizing the KL divergence between the two distributions PR and P theta. It's the same as you're trying to minimize the divergence or distance between these two distributions and doing that using by minimizing KL divergence. So with using this technique, the issues that we fall into is explosion of KL divergence whenever P theta becomes 0. So let's say, for example, I would like to, is there a chalk? So let's say our P theta distribution looks something like this. At some point, it might become 0, but in reality, for the distribution of PR that we're trying to approximate, that might not be 0 at that particular point. So a condition when your PR of any particular at any particular point x is not equal to 0, it's greater than 0, but P theta at that particular point becomes 0. What will happen for KL divergence? By the formula of KL divergence, as you know it, it will explode to infinity, and then your optimization function that you're using for minimizing this distance will not work. So one way of handling this problem is, what if you add some random noise to this P theta distribution while you're approximating or training it, and make the curve shift to, let's say this is the grayed out random noise, and you make the curve shift to a higher values, so that your P theta of x doesn't become 0 at any point. So this is one way of handling such a situation to prevent KL divergence to explode. But if you do that, there'll be errors introduced in your training procedure. Like you'll want to handle how much noise is there in your estimated distribution, and how close is it still to the real distribution. Also, while sampling, you'll face many more issues from this distribution. So why go through all this trouble? So we handle this using the second approach, which is we use another function G theta, which is trying to transform another function G, which is trying to transform Z into P theta. Here Z would be any common distribution like Gaussian or uniform, for which we know the dynamics, and we're just trying to bring it as close to PR as possible. So how do we do that? Your generator will be learning to transform Z, and so that the G theta, when it approximates using Z, it is in fact approximating P theta itself. So the training procedure of G theta will eventually be giving you what the value of P theta should be, right? So what you have to do in here, like whatever we were doing in the previous slide, but with G theta. That is, you want to minimize the distance between this differentiable function G theta with PR. PR is your real distribution that you're trying to approximate from the starting. So for minimizing these distance, how do you measure the distance between these two different types of functions? There are several distance metrics that are used for that. And while you're training, your loss function would be optimizing or minimizing the distance between these two distributions, PR and P theta, where P theta is being approximated using G theta. So the distance metrics that are used for computing this divergence or distance between these two distributions, there are several of them, and we talked about some of them previously. The earth mover distance is what we want to focus in this recitation, and is an interesting topic for you to have some knowledge on GANs in general. So earth mover distance is given by this particular confusing equation that you see in the slide, but let's see what it means. So earth mover distance is also known as Wasserstein distance. It is, you can call it short for EM distance, because what it does, informally it is representing the minimum energy cost of moving and transforming a pile of dirt in the shape of one probability distribution to the shape of the other probability distribution. So let's imagine there's a huge pile of dirt which is your PR, and you want to transform another pile of dirt, P theta, into this PR by moving some shovelfuls of dirt from P theta to PR. So, earth mover's distance basically calculates the cost of transforming this pile P theta into PR by the amount of dirt, by calculating the amount of dirt you move from P theta to PR. P theta to PR, or I would say from any point in P theta to any point in PR. So, amount of dirt you move and the distance by which you move it. So, this cost, as you can see in this equation, is simply the amount of dirt moved times the moving distance. So, let us take an example. Let us take a discrete example first to get some understanding. Let us say P and Q are representing just 4 piles of dirt each. So, P has 4 piles of dirt, Q has 4 piles of dirt, and each of these are full of 10 shovelfuls of dirt. So, if you see in this diagram, there are 4 piles of dirt in yellow and 4 piles of dirt in green. So, yellow represents one distribution, which can be your P theta, and green represents your PR. So, but the total amount of dirt present in these piles is 10 shovelfuls for now. And how this dirt is distributed across these piles is like at one point P1 in P theta, it has 3, and then another point has 2 shovelfuls, and so on. Similarly, for the other distribution Q, and we are trying to transform P1 into Q, P into Q by just transforming some piles of dirt from one to other. So, how will you do it? If you can see this diagram clearly, first let us start with the point P1. This one in here has 3 shovelfuls of dirt, right, and in Q1 it has 1. So, we would want to transform, we would want to remove 2 piles of dirt from P1, and so that it becomes the same as Q1. So, let us move these 2 piles to P2. Now, P2 becomes 4 piles of dirt, and we want to make it just 2 piles of dirt, which is the same as Q2. So, we transform it to P3 and so on. So, finally, how much piles of dirt have we moved? We have moved like 2 piles, 2 shovelfuls in one step, then another 2 shovelfuls in another step, and then in this case we moved, so in total we moved like around 5 shovelfuls of dirt, yeah. And so your earth mover distance comes out to be 5. So, that is basically just how much you moved it into distance that you moved it with. So, let us move on to the continuous probability distribution space now. Here, let us say there is a function which is representing, it is not a function, there is a set which is representing the set of all possible probability, joint probability distributions between these two distributions. So, pi of PR and PG is representing all possible joint probability distributions between the real probability distribution and the generated probability distribution. And any sample from that, gamma, which is gamma of xy, will represent one dirt support plan. So, gamma is like one probability distribution that you pick from this whole set of probability, joint probability distributions. So, gamma of x and y will be representing one joint probability distribution, and that means one dirt support plan from point x to y, how much dirt you had to move and how you moved it. So, here if you see gamma of x and y, this will want you to transfer dirt from point x to point y, so that you bring x as close to y as possible. And if you do that for all pairs of x and y in the two distributions, then you are bringing one distribution of one distribution of PG closer to the actual distribution PR. And that is why, as let us say we transform all the x y pairs, we move x's to y's to make them as close as possible. So, the marginal probability distribution of of this gamma of x and y will be representing actually the marginal distribution of y itself, of PG itself, sorry. So by how much distance you move them is just represented by the norm of x minus y. That means the distance that you move from point x to point y. And this gives you an estimate, this gives you an expectation of moving one joint probability distribution to another. And how this is useful is in the previous equation, we just do this for all pairs of x and y. So over here when you saw, we do this for all pairs of x and y, estimate how much dirt or how much earth mover distance will not be a good explanation. Let's say this expectation of inside this is just telling you what is the total cost of moving x to y. And if you do that for all pairs of x and y and sum over it, you would want to find the minimum point or the minimum total that could lead to this transformation. So that's why you take an infimum. Infimum is also like the greatest lower bound. If you want to read more about it, you should certainly look it up, but since we're short on time, I will kind of rush a little. And that's how you calculate the total earth mover distance. So finally, you will take the minimum one among the distance that we calculated, among the cost of moving all the dirt solutions as the EM distance, that is the earth mover distance. And so Wasserstein-Gann is based on this idea of Wasserstein distance, and it uses this as its loss function to train the generator and discriminator. Now, the discriminator in here, in general, discriminators are trying to classify the generated image or generated sample from generator as real or fake. But herein, discriminator is actually modeling as a direct critic, is not modeling as a direct critic, but a helper for estimating the Wasserstein metric. So how that helps in training is your generator and discriminator are not fighting against each other to prove each other wrong, but they are kind of aligning together to come to a to meet a common objective function. So, so that's why the training becomes more simpler, because you won't run into very obvious convergence issues that you run into GANs very often. So if you see by this diagram, let's say this is our real probability distribution, and this one, green one, is your fake probability distribution that you're trying to bring as close to the real one. The GAN discriminator in general would be something like this. So it will zero out over here, and then your KL divergence gradients would explode. And the Wasserstein, with Wasserstein objective function, your line would look like this, and as you can see, it will not zero out, so that your gradients do not explode constantly on any set of points. But all this talk about Wasserstein-Gann and Wasserstein distance in general, but still there are some issues that this model has, and of course it's not perfect. It does have some, like, the idea behind this model was to overcome the convergence issues in GANs in general, but still it does have some unstable training issues and some other convergence issues that we can talk about later. But for now, I'll transfer this to, I'll hand over to William, and he'll talk about more practical implementations. Sorry, thank you.
All right, so I'm gonna talk about like how to implement a GAN in real time and then how to train it. First, I'm gonna show my models for the GAN. It's a W GAN. This is the code for the how you would code the a GAN model. We're starting with having a generator here that contains with a linear layer to projection the input, and then we also have this deconvolutional layers. Here I have 5 layers of deconvolutional layers. The idea here is that the input to a generator is a random noise. So we want to deconvolve it into a image side thing. So that's why we are using deconvolutional layers here. I added batch normalization and ReLU function. There's a paper claiming that adding batch normalization will help for the generator to better extract to better generate the features for the image. I can attach this paper by giving you this Jupyter notebook, and then we have this discriminator, which is simply just convolutional layers. So it's like thinking this as like doing image classification. We have a fake image, we have a real image. We want to classify whether they are true or false. So this is like doing an image classification. And typically people use convolutional neural networks to do the image classification thing. So this is pretty straightforward. And then I'm going to talk about how to train a GAN model here. So I would like to talk about these things first. So I would like to talk about my data sets first. So my data sets is a flower data set provided by the Oxford University, and it contains a right image, which is a desired image, and a right embeddings, a language embedding. So what this network is doing is trying to generate an image given a sentence. I'm going to generate an image that are corresponding to the content of that sentence. So I have a right image, a right embeddings. I also have a wrong image, which means that this imaging has nothing to do with the given text input. So the content does not relate to each other. So that's why I have another wrong image. And I also have which I call inter-embed or wrong embeddings, which is this image might not be related to the content of the this embeddings might not has anything to do with the image's content. And then I have a text which I just want to show the attributes for every training example. So this will not go into this text information. Is just for visualization purpose. It does not go into my network. And this is my network. So this is my data set for my network. And then I have this trainer. The general idea I'm doing here is that I'm going to train my discriminator to learn to distinguish a fake image from a real image. And in addition to that, I'm also going to train my discriminator to learn that this image is not corresponding to the language embeddings. So there are 2 things I want my discriminator to learn. One is to tell if this is a fake image or a real image. Another thing is I want it to learn if it's this image is corresponding to that language contents or not. So there's 2 things to learn. It's at 2 dimensions. So what I'm doing here is that I define a de-iteration count, which represents how many times I train my discriminator. I also have this generator here, generator iteration count, which is here, which counts the times I train my generator. The idea behind this is that at the beginning, when we just started to train the GAN network, we want to train more times on the discriminator, so that discriminator can learn quickly how to distinguish a image And then later, when the discriminator is already learned something about classifying an image, we start to train my generator network to generate good images for the network. So I guess one more thing is that you don't want to train the generator at maximum speed at the beginning, because at that time the discriminator doesn't even know how to distinguish a real image and a fake image. So training at that time does not make much sense. That's why people usually train the discriminator at maximum speed at the beginning, and then later spend more time or spend more examples training the generator network. Does that make sense? Yeah. Okay, so here I said that if the generator iteration is less than 25, or the generation iteration is just exactly 500 divided by 500, then I'm gonna set the D. Sorry, this is a mistake. I'm gonna set the D iteration count equals to 100. So that means for that epoch, I'm gonna train my D generator 100 times, and then by default the number is 5. So that is to say, if the generation iteration is less than 25 or it's dividable by 500, I'm gonna train my discriminator 100 times before I train 1 times of generator, and then by default I'm gonna train 5 times discriminator and then train 1 times generator. So here I train my discriminator here. I have this right image, right embeds, wrong images. And then, so you can see here, I input the right images into my discriminator together with the right image. That gives me the real loss. The real loss means that this is the right image with the right embeddings information. So I have this real in loss. I'm gonna increase this real loss because I want to maximize the score for real image together with right embeddings, right? Remember, GAN is a minimax game, so we want to maximize the right images together with the right embeddings. So here, this mon here is just -1, which I define here. So by doing this, I'm actually calculating the gradient ascent of this real loss, which is gonna increase this real loss here. And then I'm gonna have this discriminator also input my wrong images together with my right embeddings. I want the score to be, this is called the wrong loss. I want the loss to be as low as possible. So I'm gonna do the regular gradient descent here by calculate the back propagation of it. And then one more thing is that I'm gonna calculate the loss for the fake image, which is generated by my generator. So I input the right image, right embeddings with the noise. So that's what my generator is doing, is taking a random embedding, a right language embedding together with the noise, and that way it can generate images for us. And then we input this fake image into our discriminator. That gives us the fake loss. We want our discriminator to estimate this fake images as low as possible. So we're also going to calculate the gradient descent of this one. So just wrap up a little bit. We have this right image together with the right embeddings. We're going to calculate the real loss. We want to, this is the score for the right image and the right embedding, so we want to increase that score. We want that score to be as high as possible. And then for the wrong image and for the fake images, we want the discriminator to learn to distinguish them from the real images. So we want those two scores to be as low as possible. That's why we are calculating the gradient descent for them. And then, so after I calculate the gradient descent together with the gradient ascent, I'm just gonna do the step function of it. And then, as you can see here, we have two, this is a while loop that occur the number of degenerating count times. So if it's 100, then I'm going to do this 100 times using 100 batches of my training example to train the discriminator first before I move to train my generator. By default, we train this 5 times. If it's less than 25 generation iteration, or the generation iteration is divisible by 500, we're going to train this 100 times. Again, the idea is we want to train we want to get the best discriminator before we train the generator, because that by doing that, the discriminator providing more accurate loss for the generator to learn. So next, we train our generator, which is quite straightforward. So we input the right images together with a random noise, and we get the fake images. And then we still use the discriminator to get to calculate the loss for the fake images, which is generated by the generator, and we have this G loss. Again, we are calculating the gradient ascent of this G loss because we want to increase the score. This score is that what we're trying to do here is that the generator should learn to maximize the images, the possibility for its generated images to fool the discriminator. So that's why we are trying to maximize the G loss here. This is the score for the generated images. So we need to increase the score for it. And then I have this step function that train my network. And this is and after that, this is a whole epoch of this training this GAN network. So couple things to mention here. Training a GAN is very tricky. Even you have the same network doesn't guarantee that you have the same outputs. I trained this networks for several days, and every time I got very different results. And typically the convergence speed is very slow because sometimes it just gets easily exploded, or sometimes the amount of information is too complicated to learn. So it's very typical that you have to train 50 or 60 epochs before you see some meaningful results. So normally I can get you can recognize a pattern or images after 100 epochs. So I think this is two things to learn. And then another thing I want to mention is that here we are using the language embeddings here. As we can see, the right embedding or the wrong embeddings. For image synthesis, there are a couple ways you can extract the language informations. One way is to give the language embeddings. Here this model the language embeddings I'm using is extract from LSTM. So it's a very simple RNN network that extract the embeddings. But it's worth to know that the performance of your GAN is also depends on this piece of information, the accuracy of this language embeddings. So if you can improve your language embeddings, it can also improve the general performance of your GAN network. So for example, for this network, if you can, because this one we are using RNN, just simply LSTM. So if you can use transformer or BERT network, then you can definitely get a better language embeddings that contains more accurate, more useful information about that sentence, and that way you can improve the performance of your GAN. So in summary, this image generation project, what it does is trying to generate an image from the language embeddings. So there are two ways you can improve the general performance of this network. One way is to improve your language embeddings by getting more powerful, more accurate language models. Another way is to use improve your GAN models. This is a simple WGAN network that can generate meaningful images. There are another paper called Big GAN, which is a more powerful, more robust GAN network that can generate images in really high resolutions. The problem with more powerful, robust GAN is that it takes more time to learn. The network is more deep. It contains more networks there, and it takes longer time to train, and it's also very tricky since the GAN can get exploded easily. So keep that in mind, and good luck with your, for those of you who are working on your final projects, working on GAN, good luck. I guess that's it for today's recitation. Thank you.